I'm Steve McLaughlin, Dean of the Georgia Tech College of Engineering, and this is The Uncommon Engineer.
Fine. 1-800. We live in an age.
Sounds incredibly complex. It sounds like students, you need to have abilities that span. I'm really geeking out here.
And we showed that if you spin a few more minutes, beyond just a binary test of plasma and red blood cells, because that you're spinning at such high speeds and the density of each component in your blood, red blood cells, white blood cells, proteins is different, you can actually create this layering. And in that, if red blood cells are infected with malaria parasites, that tiny parasite affects the density to the third decimal place. But because we're spinning so quickly, we can actually create a strata. And instead of looking for a needle in a haystack, it's right there in bands. And you look at it under a microscope, and it's right there.
For the listeners, it really is. It's a piece of paper that, a circular piece of paper that I think has like a plastic clip on the edge of that. As you pull the pipe apart, the paper spins.
So now Steve is actually playing with the paper fuge. And the reason I did this is because here is an experience of translating this. Because as engineers, we are often used to building things and publishing papers and saying, well, somebody else is going to take it out of the field. When you build a device that requires a training of, say, weeks or hours or days, here this training it was so simple, even a 5-year-old can do it, right?
Even a dean could do it.
Even a dean. And essentially, that is for when we think about samples and the number of patients that show up at these clinics, thousands of them, and we want to train a lot of clinical health workers with minimal training and things, you don't want to. This enables us to now one person could train the other, and this is part of the translation. And that was what I wanted to show, that the effort required, how hard was it to pull this? Often it's with these things, the reason I bring these things and I kind of tell people to use it is, you could read the paper and then you use it and you kind of understand that there is much more in the engineering that goes in to enable real world application rather than just we can all write papers, but that other gap is where a lot of technology fails, and we try our level best. So when we published this paper, we had 15 pages of supplementary information just describing the mathematics. And one key thing that we realized is the reason these soft, flexible, pliable strings enable us. And so this answers the question of what is the most efficient way to convert, translation movements of your muscles into rotational movements. It turns out that using rigid components such as in salad spinners or your egg beaters, you're using gearing mechanisms. What we are exploiting is actually the flexibility of strings. And the key thing, the theory, the physics that I use was actually used from DNA supercoiling. Because what happens if you watch very closely is that the strings actually go from just twisting to actually forming supercoiled structures that displace out of plane. And that enables these strings to act as springs that store energy.
To get to 125,000 RPM.
Exactly.
Yeah,
And so that was kind of the aha moment that, look, the physics are complex and you figured out an interesting way to actuate things. And now people have built on this to new applications from generating electricity because, and you can, that's the cool thing. It's so simple that, and it's cheap that you can think of 10 different things you could do with it. I feel very lucky because Georgia Tech is one of those places that attracts people who really want to solve problems and are very open-minded and curious, which is a key recipe because curiosity, curiosity drives a lot of our stuff and the problems we choose. And so the students come from backgrounds, so from physics, from bioengineering, chemical engineering, of course. And I also find that so far in this short duration that we've been here, some of the students have multiple degrees, so minor in, say, computer science or a minor in art. This is the other part of my lab, which works in organismic biophysics and where we look at organisms and specifically from the lens of extreme biology, asking the question of what is a fast animal in nature? So if I asked you that, what is the first animal that comes to you?
I think the cheetah or something like that, yeah.
Yeah, so that's kind of the common notion of what we think of as fast as cheetahs and diving birds, for example, and hummingbirds. And it turns out, and this is a growing community of biologists and engineers, and who, for the last decade or so, using high-speed imaging, which is modern technology, has been able to look at different organisms, and found that there are organisms such as a mantis shrimp, a trapjaw ant, and even jellyfish, nematocysts from jellyfish, that achieve accelerations of almost 10 million meter per second square in nanoseconds. Compare that to a cheetah's acceleration, which is about 10 meters per second square, or Usain Bolt for that matter. Kind of forces your notion to ask, what the heck is a fast movement? And, fast in what? Velocity in terms of acceleration? And so it turns out acceleration is actually an interesting question to ask. So we wrote a paper earlier in the year on analyzing hundreds of these engineering systems and biological systems to find universal physics and to show why, as engineers, we haven't built these tiny robots that, Feynman and other Asimov. We've been thinking about this for 60 years. There's plenty of room at the bottom. But where's the robots that, you swallow as a pill and go through your bloodstreams? And so the paper outlines that there are some challenges. That's why we haven't built these tiny robots. And of course, it's a very complex thing, but some of them relate to power delivery. How do you store energy and deliver it at small scales? And that's kind of a challenge in building autonomous robots. And so we look at it from a biological system to discover how these systems accelerate very quickly, because if you just take derivative of that is just power delivery. And so that's kind of interesting. And you realize that biology has all kinds of unusual motors beyond muscles to release and store energy in materials, from very complicated materials such as resin in mantis shrimp in crustaceans' bodies to geometric latches and springs. And so I was a year ago, or 2 years ago actually now, in the rainforest, in the Amazonian rainforest in Peru, where we were doing some field work testing our low-cost devices. And I took a day off because as a child I'd always want to go to the Amazonian rainforest, And so we're there on the last day. One of the guides showed me this tiny spider. He said, "Look at the spider, and it moves really fast." And indeed it did. I couldn't capture it with my iPhone because, it only goes up to 200 frames per second in slow motion. And so I came back thinking, it's like, and I Googled, and, the best thing as a young scientist is when you Google and you see, holy smokes, there's no mention in the scientific literature. Uh-huh. It's like in 2018, when do you ever get to Google an insect and see there's nothing known about this? So, well, I hired a postdoc, and this year we went back to the Amazon rainforest, equipped now with high-speed cameras, and we discovered the spider that we are calling the slingshot spider. And we're writing this paper, so I don't want to say too much, but the gist of this is that it achieves accelerations of 600 meters per second square. And so we're kind of going piece by piece, trying to answer the question of what the heck is it doing? How is it doing this? Why is it doing it? And we have pretty good answers for some of these hypotheses. And to the best of our knowledge, this is the fastest movement by an arachnid that we've kind of recorded, movements of in less than millionths of a second. And so there are 2 points here. One is, you said, why should an engineer care? And, the engineering part is, silk is one of those biomaterials that has, if you think of a biomaterial that has inspired engineers and material scientists more, silk is up there. And here we've realized that silk is, you think of it as strong as Kevlar, but we realize this silk in this particular case, in this rainforest spider, is not just strong in Young's modulus, but actually is very, very elastic, and acts as a very complicated three-dimensional network of springs, and similar to what you would think about Leonardo da Vinci's catapults, but in 3D. So that's one. And the second is kind of we do a lot of outreach in Lima with a lot of high school students. And, when I ask the same question over there, these kids will tell me the fast movements are cheetahs. They don't have any cheetahs in Peru, but the kids are reading textbooks from France and from Europe. And I try to illustrate to them, look, your backyard is full of incredible biodiverse, living creatures, both insects, arachnids, and all kinds of things. And here's a tool, now this low-cost tools that you can use to actually explore your own biodiversity and discover things, because now you can. In 2018 you still can, and now you have things you can put in your backpack. And so we share with them, and the kids, that's kind of the second part of this, is to kind of encourage them that we lose so many organisms every day that go extinct. We just don't know. And to me, what's beautiful about this is we all care about encouraging hands-on science, but often hands-on science implicit in there is you give them, tools. Information is free on Google, right? But how do you give them the hardware? And here we're turning these kids into problem solvers, because you want to do synthetic biology and do CRISPR, but you need to build your own tools. And that's kind of to me, this is our second device that we're kind of writing up now and sharing this. So there are many different lessons here in teaching, students to be problem solvers, but also participating in the whole circle of science, is going from a brainstorming idea from a whiteboard to building thing and to writing a paper, because this high schooler now knows much more about, sharing his science through the language that you and I do is papers, and enables them to participate, right? And encourages the other high schoolers to be problem solvers as well. The aha moment with all these things is one night we do one experiment. I was like, holy smokes, it works. But then we spend years trying to figure out why the heck does it work? Because these kids will bring me data that looks on point, right? 2,200 voltage with a standard deviation of only like 100 volts. I was like, I don't believe this. Are you doing your measurements right? And so we had to understand the physics. Turns out that it's independent of user, because a lighter is a lighter irrespective of who fires it, a kid or a grandmother. That's because the force is dependent on a spring and the spring constant inside. And so it's till you actually understand the mechanics. It turns out, who studies the mechanics of lighters? We had to. So, that's part of our paper. The reason for this is important, because the next step we're taking this is into gene-based vaccine delivery. And you need to control the voltage for mammalian cells, and that's different because these cells are not, order 10 microns versus bacteria, which is a micron. You need a different voltage field. The spring constant allows us to change that, and that's where the science comes. We understand why the heck it works. And then the same theme applies where I just showed you that we translated. So now we share these designs and devices now, and people in high schoolers in Taiwan tested it across Georgia to different schools, and so people reproduce our results, and it only takes a week because we ship them one, but we just give them the 3D printed files, and these kids download it. The demonstration over here is that, of course, our science is reproducible across the ocean, but there is also a need. I initially misjudged how not easy, but how much hunger there is, and how much the high schoolers can do synthetic biology, but are often restricted by scientific tools. So the Frugal Science is again a workhorse tool that we're developing, that we're not going to tell them what's a living sensor to make, but we're going to give them the tools that get them to unleash their imagination and creativity.
Even a dean could do it. 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 Even a dean could do it.
Typically, as engineers, often we love to think, what if you had infinite resources? What if you had $1 million or $1 billion bucks? And that's kind of where I come from in the Bay Area. It's like, if I give you, $1 million, what can you do? Can you change the world? And we like to take the exact opposite approach. And, the analogy my colleague was drawing, what would Gandhi do? Or how do you think if you had nothing? What would you do with bare minimum? And it turns out, for some of the problems we care about, that is the reality of the situation for a lot of people, where they might not have access to infrastructure, electricity, basic things that you and I would say, oh, just plug it into the wall, but there's no plugging in, there's no batteries. What do you do then? And that's kind of the constraint we deal with.